All right. First of all, thank you guys for coming on a Sunday rainy morning. I appreciate coming you over. And I saw the last presentation. It was really beautiful. So don't expect this presentation to be as beautiful as the last one because I'm really an immature presentation maker. So yeah, sorry for that. All right. So I hope you will guys enjoy because this is the last session before lunch. So I hope I won't make you guys drowsy before going for lunch. So okay. So a little bit about me. So I'm currently working as a research intern at Nokia Bell Labs, and I'm working on next generation networks and lunar networks. So basically, I'm creating a next generation network for your home, for offices, for big Amazon warehouses, and lunar networks. I'm also making some networks for moon, for transmission of networks from Earth to moon to create better communication between them. And my normal day is I normally read a lot of papers and then I try to automate certain things using machine learning and whatever things I know. Previously, I was working in India with a startup over there under Microsoft Accelerator, so I was doing that. Okay, so before starting, I would like to conduct a simple experiment, and I would like you to see this video and have a little bit of thought on that. Okay. Yeah. Wait a second. So this guy over here, if you can see, the black guy, you see, that's the player, and the other green guys, those are the enemies. All right. And if you just see that, the guy's getting hit and he is not doing anything. So, he's not actually responding. So the player who is actually playing is basically, stupid. He's not doing anything. Let's do one more time. Now he's actually responding. See, it killed all the players. Another time, let's kill again. So what was it? So that kind of learning, what we call is as the reinforcement learning. So when we classify machine learning, we divide in three categories: it's supervised learning, unsupervised learning, and reinforcement learning. Reinforcement learning is kind of a rewards-based machine learning algorithm. So there's an agent and it responds in an environment. So whatever action the agent will take, it will get a reward for each of its action. And whatever the reward it will take, it will understand, okay, whether this action which I took, was it rewarding or was it penalizing the action? On the basis of it, it will learn the whole environment. It will learn, okay, if I am at this stage, what action I should take which will give me the maximum reward. So the goal of the agent in the whole reinforcement learning is to maximize the rewards at the end of an episode. By episode, I will mean that the whole session. So if I'm starting from here and I want to start from here and I want to go back home, what action should I take which will maximize the reward by the time I reach home? Yeah. So this is the whole major framework which revolves around the reinforcement learning thing. There's an agent, there's an environment. These are the two main components in the whole reinforcement learning. An agent takes an action A in an environment. On response to that, the environment gives two things back to the agent. It's new state. So suppose I'm standing over here, I move forward, I'll end up being over there. So that's my new state. So the environment will give the agent, okay, which new state you end up in. And environment also give it the new reward. Okay, you took an action, was it rewarding? Was it penalizing? So the environment has to be a very subtle kind of environment so it can understand the agent actions as well. So if you're having a game and just playing actions and the environment is not giving you any reward, that doesn't make any sense. So you have to build an environment and an agent. So if you're creating, let's say, a game, then it's not like you have to create the whole game and then just have a player. You also have to create an environment. So if an agent takes an action in the environment should be able to give the new state and the rewards as well. And also you have a policy which revolves around the agent. So you can have a multiple policy. You can have the agent only to maximize the rewards, or you can have the agent only to take minimal number of steps. Yeah. So you can have a different policy for the same environment for the same conditions. So there are two ways of learning in reinforcement learning. One is called Monte Carlo learning, which is very famous. You must have heard of MDP, Markov decision process. So there are you have multiple states, and when you jump from one state to another state, these are called Markov decision process. These are Markov states. And when you jump from one state to another state, this is called Markov decision process. So in Monte Carlo method, it's you collect the reward and you get the whole reward at the end of an episode. So let's take an example. I'll give you an example later on. Let's understand this first. And the second case of learning is the temporal difference. in which you get the reward at every step. So you can see the second one is much more, profitable for us because we are getting rewarded at each step. So we can assume, okay, if I took a step wrong at the same point of time, I will get to know this step was wrong. So I'm getting the information at the same point of time. But in Monte Carlo, I will have to complete the episode, and then only I will get to understand, okay, this whole step was wrong, and then I have to again start from the fresh. So let's take an example. So our agent, let's say, is is a mouse, and there is a cat in the whole area, and this is our whole environment. So if you take the Monte Carlo approach, the cat can start from here and go all the way to be eaten by cat, and that's not what we want. So Monte Carlo will say, okay, this whole thing was the wrong step, but here is a reward for us, the C's. Monte Carlo will say, okay, this whole step was wrong, you should not take this. But in temporal difference, what will happen is you take this step, you get a reward, good. You take this step, you will say, you're not getting a reward. So you have to take this step again. So temporal difference will give you information on each and every step, what step you should take, what step you should not. So temporal difference is what mostly we use in reinforcement learning methods. Again, in reinforcement learning, there are two phases what we can define. Previously, what we studied do different kinds of learning, Monte Carlo and temporal difference. And here we have like two different phases. One is the exploration phase, and one is the exploitation phase. In exploration phase, what you do is you allow the agent to really explore the environment. You are giving the reward, but then agent is keeping the information like for all the rewards he is or she is getting. But at the starting, the agent doesn't know the environment, right? So that's what we call as the exploration phase. When I came to Dublin, I didn't know anything. So I was like roaming around, getting onto wrong buses. That's how I got to know, right? That was my exploration. But after like 1 year or 8 months, I know in Dublin, and now I can exploit all the buses. I can use my leap cards most suitable number of cases so that I don't spend that much of money. So that's my exploitation phase. In exploration phase, at the beginning, the agent might take like stupid actions. It might go and keep on revolving under the same bridge or whatever you can say. But after some point of time, when the agent has a bit of understanding of the environment, it might slowly go into exploitation phase, and it will take only those actions which are profitable in terms of rewards. So these are two learning phases of the agent in a reinforcement learning environment. Again, there are different models in reinforcement learning. There are model-free algorithms, there are model-based algorithms. One of those famous algorithms is the Q-learning approach. What happens in Q-learning is like you create a Q table. Q table basically a matrix of state action pairs. I will also tell you how that matrix is being created. So you initialize the Q table, and then you choose an action. Okay, you choose an action, you perform the action, and you get the reward. And what do? You take a step. You were at step S. You took an action A. You went on to step S dash. Let's say S prime. Okay, and you got a reward. And what you will do for that previous step, you will update the Q table. You will go back to the step, and you will update the Q table based on the reward you got. And that's how you keep doing it like multiple times. That's why the training algorithm takes like days or months of training, because the whole Q-learning table is quite big that it takes a lot of time to explore all the actions for all these states. So to like fully populate the Q table, you need to like give a certain amount of time to the agent, basically like to fully understand the whole environment. And then you repeat the whole training again and again. At the end, you have like good Q table, which you can exploit later on to take only those profitable actions. So let's say this is our Q table. On the first column, you have all the states mentioned. Let's say in our environment, you only have like 2 states, all right? And in the first row, you have like actions, all the possible actions which an agent can take. And how do you update the Q table is based on the modified Bellman's equation. So suppose you are at state 1 and you took an action A2, you end up being in a state S2. Then how will you update this value? Because you took an action S2 when you were in state S1. Then how will you update this one? Is by this method. It's a pretty long equation. So basically what you have to do is you have to keep the learning rate. Learning rate, which you can understand, is like learning rate oscillates between 0.0 to 1. So the higher learning rate, the agent will understand or like learn pretty much fast. Discount factor is there just to maximize the future rewards. So it is possible that I start from here and I go to O'Connell's Bridge and take a bus to Blanchardstown. Okay? Or is it possible that I go from here and I don't know, I go to the airport and then take a car or anything to Blanchardstown. So there are 2 ways of going there. One is the thing is like how discount factor will tell me what is the maximum future reward which I'm taking for that. So suppose let's imagine like there are two doors, okay, this door and this door, and they don't have any reward over there. Let's say there is a like plus 10 reward on this door and there's like 0 reward behind this door, okay. So what will the agent do is like, okay, definitely this door is giving plus 10 rewards, but this door has a plus 100 rewards. It's behind its second door, okay. So there's a maximum, there's a like a big reward waiting behind like one more door. So what will it do? It will also maximize the future reward. It will also take care of the future rewards which the agent can take, okay. So you can say is the estimate of optimal future value. So the agent has to understand, okay, what is the maximum reward it can take for each step. So it is not only calculating for the next action, but it is also evaluating the future rewards which it can get in the future as well. Yeah. So this is a pretty big equation. If I end up explaining all, you will all just end up being browsy. So this is the whole modified Bellman's equation, and you also have a reward over there. Yeah, this is it. So you keep on doing that, and that's how you keep on updating the Q table. So now let's say we have the whole Q table. Now what you will do, the agent will, let's say, in state S1, what action it should take that it should be in S2. Obviously, it will take action A2 because it is giving the higher Q value, right? So that's how you exploit the Q learning algorithm, and that's how it is being formulated. I will show you a simple example to let you know. So let's say this is our environment, okay, and this yellow cab is our agent, okay. Now the goal of this agent is to and these all are like say destinations or the people which the taxi can take in. So the blue one represents say, okay, this passenger has to get in the cab, and this is the final destination of the passenger, okay, and this is their environment. And I did not create this environment. I'm basically using So I'm basically using OpenAI Gym, which I will tell you by the end of this presentation. So there are like multiple environments, so you won't have to create your own environment to give you the new state or the reward, because that's again a hectic process. And if you want to create a whole new big project, you can create your own snake game, you can create your own like Flappy Bird, create your own game. You have your new state, and then you can train the algorithm to create a Flappy Bird monsters which can go on to like multiple levels. So what I was doing over here. So again, I'll tell you again, the agent goal is to pick this passenger and drop it over here. Now let's run this thing without any training, okay? So what it is doing, you can see it is right now at this stage, and it went up, still there, still there, still there. It's taking random action. It doesn't know what it should do. Now, but then here is our algorithm. You see? Now how we are training it, like for each episodes, what we have instantiated over here is like, let's say we are giving it like, we're training it for like 50,000 episodes. We're gonna train this agent for 50,000 episodes, but we don't tell them, like, we don't tell it like, okay, blue is the passenger and purple is the destination it should go. It will learn on its own, okay? And these are the other parameters. Epsilon is basically epsilon min and epsilon decay is what I'm doing is like I'm going from exploration phase to the exploitation phase. But I will not do that because I'm not doing that in this thing right now. So what I'm doing is for each episode, I start this environment.reset is basically resetting the whole environment, okay? I reset the whole environment, and okay, I also set this maximum state. I tell the agent that in 50 steps you have to complete the whole process, okay? So what it does, it takes a random action from the environment. The OpenAI Gym will give you a random action, okay? It takes the action, and it will give you the next state, the reward, or whether it is done or not. Done, it will give you a Boolean value whether it's true or false, okay? And you keep on adding the score. And then you use the whole Bellman equation to update the state. So this is the new state, and that was where's the old state? Anyway, you have the first state anyway. So you first instantiated the whole Q table. How do you instantiate it is basically, yeah, over here. You see, you first from get the environment is like how many possible number of states the environment has and how many possible number of action it can take. You can see this is the 500 total states and 6 actions. What are the 6 actions? It can go up, left, right, down, pick up, and drop. Yeah, total 6 actions. And this is the whole queue table, basically an NumPy array. Okay. So let's say it is currently at state over there, whatever the environment gives us on resetting the state. Then we update the whole queue table, and then we again set this state is currently the next state. We basically do the simple programming. And then we keep on doing it. And let's say after, let's say 2 steps, it is done. Let's say randomly, after 2 state is done, we break it, and then we perform the next episode because that episode was done, okay? And then we keep on training it for like say 50,000 episodes. Now let's see what comes out of it. So this is the queue table, what we get it. Yeah, and that's how you can see there are still some of the rows which are like empty right now. I did perform the training before coming here because it will take a little bit of long time. You can see still like some of the queue table is still empty because even 50,000 step cannot fulfill the whole the whole queue table. It will take a bit more long time because there are like so many states and so many actions. So it will have to explore, okay, at this state what action I should take, at this state what action should I take. So this is the whole queue table updation. Now we will see what happens. Now if I do that, right now, let's say, okay, I'll do this again. It started with the pickup passenger only. Okay. Yeah. Right now, it started at this state, okay? Correct, taxi is here. Now what should be the next step? The taxi should go over to the blue passenger. And that's what it's doing right now, okay? And what it should do next, it should take the passenger from here and it should drop it over at Y. So that's what it will take. You see, it started from here, picked up, see, pick up, okay? And then start from there and keep on going down, down, see, drop off. And that's the end of the episode. I'm just running it for 1 episode. Now you can. So that was my policy. My policy was to train the agent just to like pick up and drop off at the correct position. Your policy can be different. Your policy can be to minimize the steps. To minimize the steps, the agent or the car has to take from pickup to the drop off. So you can have multiple policies on that. So that was queue learning, basic example. And so that's how the queue learning works. Now let's talk about another algorithm. Let's say deep queue networks. Now let's say you have a game, you have like Dota 2, which is very popular right now thanks to Google Mind, DeepMind. Now let's say you have like humongous number of states and action pairs because a game can be like number of states because you have like so many, let's say GTA 5 or anything like that. You have so big number of states and so many actions which you can take. You cannot build a queue learning table out of that because that will be like, monstrous. You cannot handle that. That will take larger time to compute, compute the Bellman equation, and then you keep on updating that. So that's a hectic process. So what you do in terms of that, you use deep queue networks. So basically, it's replacing the queue learning table with neural networks. All right. And in terms of queue table values, what you have is the weights of the neural networks. So you don't have the queue values, but instead of that, what you have is the weights of the neural networks. And what you do, okay, I'll tell you that. So deep queue network got famous just because of this paper. This paper, I think, got released in 2014 when Google basically told you, okay, it developed an algorithm which can basically solve most of the Atari games it was following. And you can read that paper. I will also post this presentation somewhere. They'll tell me to. You can read this paper. This is a brilliant paper, and many of the reinforcement learning people who are doing reinforcement learning are following this paper. See this again, Bellman equation. Now let's consider this game. How will you actually make this game? Because you cannot make this game out of queue learning because so many states, so many actions could take. So how you can solve this with queue learning thing? Sorry, deep queue networks. What you do, you don't need all of this image. What you can do, you can crop this much. Yeah, this much from the bottom, this much from the top, because you don't need that much of pixels when you are basically computing it. So what do? You crop that and you pre-process the data. Second thing is you stack a couple of frames together. Why you do that? Any idea? Just because to get a motion, and just to give the computer a sense of motion. If you just give this a single frame as an input to the neural network doesn't know where this ball is going. But if you give the neural network, say like stack of 4 frames, it can give you an idea. Okay, this ball is moving like towards the right hand side. So just to give a sense of motion, you have to stack the couple of frames together and feed it to the neural network, and then perform the prediction. And then you keep on doing it again and again and again and again. So how does deep neural network works is like on the left hand side, you give them the inputs, and what the neural network does on the right hand side in the output layer, it will give you the all possible actions, basically the probabilities of all the possible action you can take. The action with the highest probability is the one you should take. All right. So this is how it works. So you take a stack of all 4 frames together. You perform CNN on that, and then you flatten it, and then you put as them the inputs, and then you feed to the neural network. So you're feeding it, and these are all the possible action which the agent is possible in the environment by the agent. Okay, so it will give you the probability of all the action. Now you can see one more time. So it's doing dot. How many of you are familiar with like neural networks, by the way? Most of you. Okay. So how many you can see the model is performing dot fit and dot predict at the same time, right? Because it's doing dot fit. Okay, you have like 4 frames. You're dot fitting it into the neural network. It's performing some action, and then you dot predict to get the highest probability of the action. So you're performing both the same time, dot fit, dot predict, most number of times at every step the agent can take, and the agent can take a lot of steps because there are like large number of states. Yeah, so that's the problem. So too many operations happening at each step. Now, can anyone tell me a solution to that? Because if you have this, if you have dot fit, dot predict at each step so many number of times, it can confuse the whole neural network, and your neural network end up being a total waste. So what do you do? Anyone? No. Sorry?
Copy of the neural network?
Yeah, exactly. So what you want to do is like have 2 neural networks, obviously. So one for like dot fitting and one for like dot predicting. Why do we do that? Just to have like do not have a partiality. So let's say you took first 4 frames, you put dot fit, and then you dot predict. Okay, the weights were like totally biased. Let's say 0. Okay, you do dot predict on weights of dot 0. If you do dot fit on the same neural network, the dot predict will not be the same as it was done before, because the cases have changed, the weights have changed. So you want the dot predict to be happening on the same weights. All right. So what do? You keep a model for dot fit, and you keep a model for dot predict. So let's say for like 10 actions, you keep on fitting it on the same network, and after say let's 10 iterations, you put on the weights, and then you do the dot predict. I know some of you are going to be like, okay, what this guy is talking about. All right. So let's do one thing. So what you do is you create 2 models. The first model is doing for dot fit at every single step, and the second model is doing for dot predict at every single step. So for let's say for first 10 iteration, what you do is like you keep on fitting the first model, and you keep on predicting for the second model. So there's a consistency is there, because for first 10 iteration you are doing the dot predict on the same model with the same weights. Okay, and after say 10 iterations, what do? You put on the weights again, because after 10 iterations, the previous model, the original model that has been somewhat modified, yeah, that has some kind of like intuition what the environment is, and that has some kind of intelligence. So what do you do after 10 iteration? You set the weights for the dot predict model as like the dot fit model. Yeah, I'm making sense, or I'm just making dot fit dot predict. Yeah, hope that makes sense. So that's what it goes like, and then you have like a consistency, and that's how the neural network can learn better. Second thing is what you need to do. That's a bit of high level. What you need to do is like a replay memory. I forgot to add it over here. I should have. But replay memory is basically, let's say you have a game with say 50,000 states. Okay, and let's say you are playing a Flappy Bird game. Okay, so you must have seen in Flappy Bird you have like level 1 with like very less number of tiles, very less number of pillars. And when you go in level 10, you have like more number of pillars. So what you do, if the neural network is going on training for like continuous, by the end of like let's say 10th level, it will memorize. Okay, it will memorize just for the level 10 because that's the latest. So what you need to do, you also need to make it experience the level 1 states as well. So you keep on doing that because so that neural network doesn't memorize the states. You do not want it to be doing that. Overfitting, you don't want that. So replay memory, another key thing. So the reinforcement learning is also being used in self-driving car and other cool things as well. So let's take the case of self-driving car simulation. So you have a couple of states in the, like say like traffic lights, green and red. Is there someone standing in front of me or behind me? Can anyone tell me another state for self-driving cars? Is there a car beside me or not? That's again one of the states. Action which it can take is, again, accelerate, brake. These are one of the possible actions. And again, you keep on moving the rewards, whether it does not damage the vehicle, it does not violate the traffic laws. If it is doing just fine, then that's the state, or that's the best possible policy for the self-driving car. That's it for us to take. So that's the whole thing which self-driving car revolves around. So this is basically a simple explanation how it does that. But yeah, reinforcement learning, that's what drives self-driving car as well. Another few applications of reinforcement learning is like playing cool games like chess, Dota 2, and AlphaGo. They all has been done by reinforcement learning. Reward can be different. It again is not to be instantaneous or delayed feedback. Again, Monte Carlo and temporal difference. Yeah, it doesn't have to be at every step. It can be after each episode. Again, in robotics, how a robot can learn to pick up the objects. You can also do that. And other cool stuff in manufacturing. In Amazon warehouses, suppose you have like a couple of drones, Amazon is putting like these kind of things. So what we at Nokia is also planning to do is like in Amazon warehouses where you have a couple of robots moving around, how a robot can learn to like pick up one box and give it for the parcel or whatever things. So how you can also train the robots to do that and other stuff. So yeah, that's it from my side. I hope you guys enjoyed it.